Thank you all for coming. This is in some ways, I guess, a continuation of a talk I gave here in this quantum space-time seminar series some time back, based on a recent paper which came out maybe last week with Aninder Sinha. I was a little hesitant because it's a somewhat technical paper, and I didn't want to inflict all the technicalities on people, but maybe I will try to give a bigger picture and keep the technicalities to a minimum.
Rajesh, maybe I could just say that we've been having a journal club every Friday.
Okay.
Ashok has been joining in, trying to understand all the technicalities of the bootstrap. So
okay. Okay, fine. Very good. The idea behind this approach, which we have been developing, is in some ways reviving an old idea of Polyakov from 1974 in somewhat modern incarnation, and sort of enhancing its power using the techniques of Mellin space, which is why the title. And it is somewhat orthogonal to the usual bootstrap approach, in which one demands crossing symmetry invariance of the 4-point function when expressed as a decomposition in terms of the conformal partial waves in any given channel, an S channel or a T channel, in terms of the conformal blocks. So here, in the approach that Polyakov suggested, one tries to start with an ansatz for a crossing symmetric 4-point function, a manifestly crossing symmetric 4-point function, expanded in manifestly crossing symmetric way. So start with an ansatz like that, but then try to ensure that this 4-point function satisfies the requirements that in any given channel, when you expand it, it has all the right operators that can appear in that particular channel. So the consistency with the OPE in any given channel is what you impose. Namely, in more concrete terms, and as we'll see, you require that in any given channel there are no operators which are not in the physical spectrum, whose dimensions are not in the physical spectrum, and which we would so there will be, as we'll see, numerous, if you work in position space, there will be numerous spurious power law dependencies, which you will have to, the power law dependence in position space is determined by the scaling dimensions of the operators that are exchanged, and you would want those spurious power laws to be not there, and demanding that is the constraint in this approach that you use to fix the conformal data, namely so we want to, the goal is, like in all bootstrap, to fix the conformal data, which is the spectrum and all the 3-point functions. So the only question is, what are the constraints that you apply to fix this? In the conventional bootstrap, you use crossing symmetry, but the consistency with the OPE is manifest because you are expanding in the operator spectrum in terms of the conformal blocks with the right operator dimensions in each channel. But here you are preserving crossing, you are sort of building in crossing symmetry from the beginning, but trying to require consistency with the OPE in any given channel. So that's the broad idea. So it will play a role in various places, like in the usual bootstrap. For instance, the positivity of the C, well, even before that, the fact that you would factorize the 4-point function into 3-point functions with the right residues or so on is built into the meaning you're crossing symmetric ansatz. You will build that into it, that it has those properties. So and then you can choose to also demand positivity of the square because when you expand, the squares of these appear, and so that kind of constraint also enters. That's
because otherwise, if I might aim was to use some basis and crossing symmetric and write down the 4-point function that has the right tail in it, then monomials of U and V will form equally.
Yeah, so you want to do a little more. You want to use your ansatz in such a way that you at least build in some of the, so your basic building blocks in your ansatz already satisfy some properties so that you're guaranteed that there will be an expansion in terms of conformal blocks and so on. So those things you will try to build in already into your ansatz, and fact then for that there would be a factorization, except that it would seem as if there are additional operators in the spectrum compared to what you would naively have thought.
Just to understand the concept, you are saying there is a trivial way of satisfying both these things?
U to the n, v to the m plus u to the m, v to the n. You can write down an ansatz like that.
And what goes wrong with it? You say unitarity is? Unitarity is not totally not naive. And it's not true.
In general, you will not, because it will not.
It would be difficult to implement
because you want to ensure that the coefficients of the descendants, all of them have the right residues, which are this thing. And the conformal block, if you expand it manifestly in terms of conformal blocks, that gets assured, and because you have the right contributions from the descendants compared to the primaries.
Just make one comment just to see how this can be written in a very trivial fashion. So you have this U and V, which is a ratio of two things, right? So in general there are three combinations, A, B, C.
Yeah.
U can be thought of as A over B, UV can be thought as B over C, C over B, let's say, these three things. Now if we take those three variables, which are essentially x1, 2 squared, x3, 4 squared, and so on, and write down a homogeneous function of ABC that is permutation invariant, then that would satisfy crossing as well as we have the right to.
Yeah, I mean, if you just wrote like that, I thought this is what you meant.
Yeah, but what I'm thinking is there is a, but yeah, you probably would have.
Then you would have to, yeah. So you can write down with the other one as well. Yeah. So, but this sort of an ansatz will not will be a somewhat poor ansatz to begin with itself.
But just try to understand precisely what. So I thought conformal blocks were just a basis for crossing invariant functions, right? So presumably.
No, conformal blocks are not crossing invariant. No, what do you mean crossing invariant functions?
Not crossing. Sorry, the things that obey the one identity, things that obey the conformal one identity.
Yeah.
So anything that's written in terms of U and V automatically obeys the conformal one identity. So any function of U and V can be, in principle, presumably expanded in conformal blocks. But I suppose what would go wrong is that you'd have a continuum.
And in general, positives will be this thing, yeah. So you want to have a minimal sort of an ansatz in which you have not too much more than the data that you expand. Yeah. And even the thing beyond that also, the and then each of those coefficients will in general be some random coefficients. They won't have any positivity property or anything like that. So, so we'll so the basic object, as in which all of you are familiar, is the sort of the non-trivial part of the 4-point function as a function of the two cross ratios, and the ansatz following Polyakov is to write this, and I'll write it now in position space. So this was the form in which we were originally viewing it, but as we'll see today, there's a certain ambiguity in writing even these Witten exchange diagrams. These are the things which are supposed to be the functions that you would compute using an auxiliary ADS-D plus 1 and writing it in terms of the bulk-to-bulk propagator, bulk-to-boundary propagators, and so on. So, so of course, when you sum over this, that is a set of crossing symmetric. That's a crossing symmetric quantity. But as I will mention, in general, it seems to be important to consider also a family of these so-called contact diagrams, which are which I'm labeling by. So here, these diagrams are labeled by the delta and the L, which is exchanged over here. But here, I'm parametrizing in a way which I will probably say more later. But these are essentially diagrams of this kind, and these are the kind of contact diagrams in which, so of course there's no delta and L, there's no exchange particle, but there's various kinds of derivative kind of interactions you can have over here. So that's what, in a way, this I is labeling over the various higher derivative corrections. So the simplest one will be if you had a phi to the 4th interaction in the dual bulk theory, but you could have also have had grad some higher d phi to the 4th kind of interaction, etc. These functions are also, people have computed them in position space as these so-called d functions and so on. And so this is the sort of ansatz we will work with. I should say, sorry? Sum over I, very good question. In principle, there's no reason to expect it to be finite. There may be other criteria, and this is one of the things that we still don't have a good answer to, of which will, I should say, in various, there are controlled cases, which I will maybe get to by the end, in which you will be able to truncate to a finite number of terms over here in a controlled way. But in general, we don't know the answer whether we will need to consider an infinite number of these, not, and what would be the criterion. I suspect there will be a criterion which will at least constrain these in some way, which is to do with the behavior in, at least in Mellin space, in the dual variables at large S and T. So, but yeah, so because otherwise these in principle can be unbounded, and you can have somewhat bad behavior, but let me come to that later. Yeah, so that's also a very good question. So in the examples that we'll distinct, the alpha i's will be determined in terms of the rest of the conformal data, and they should be. I mean, and there's a certain sense in which, so they should be. They're not part of the, they're not independent. The conformal data is just this. They should not, in general, be independent. The complete criteria which fixes them in terms of these conformal data is still not is still unknown to us, but except in some controlled cases.
Sorry,
Yeah.
a trivial question, but the W
Yeah.
delta L is literally what you would get by doing
Yeah.
ADS calculation.
Yeah. So I will come to that a little bit more, but at this stage, let me just say yes, that with the bulk-to-bulk propagator, bulk-to-boundary propagators, and so on. So the,
What is the mathematical statement? Is the statement that this particular set of functions is not a complete basis for the kind of functions?
which this one?
Yeah.
It depends on what you mean. This is some part of it has to do with what you mean by this functions, and this is where I will come to. There is a certain ambiguity in defining these Witten diagrams, which can be traded for contact terms, and.
It's not the ambiguity that arises in the transition to the Mellin space.
Yeah, this is just a physical ambiguity that is there in this thing. So so we will choose a particular canonical form for these in Mellin space, and then try to parameterize the rest by this.
I mean, from the bulk, it does seem that there should be a distinct possibility of contact.
Yeah,
right?
yeah.
Because the exchange of particles is a different
Right, right. So it's very unnatural in some ways to not have it, but yeah. Yeah, the bulk interpretation I do not want to go into because I have talked about this before and I don't have anything further useful to say about it. We will see the relation, if I get the time, between the conventional ADS-CFT, this thing, and this procedure, which is slightly different. I must point out maybe one difference, that this delta and L is the sum over the whole spectrum, sum over entire primary spectrum. This does not mean this is not just the single trace operators which we conventionally sum over in the ADS-CFT. When we make such an expansion, it is over the entire spectrum, and this will be important, and we'll see how doing this will actually reproduce the same answers as you get with the single trace spectrum in a somewhat non-trivial way, in a somewhat different way from the way it usually does. And so it's not quite the same as a conventional bulk.
And just to say, this is the thing that makes it a bit surprising that you have to keep both. From the usual ADS-CFT point of view, that
Right.
thing takes into account double trace exchange.
Yeah, but it is not unusual if you think of it that we are applying this to a generic CFT where there is no notion of a single trace, double trace in any good sense.
So that also sort of makes clear that there should be the double data.
Yeah, yeah. You mean this sense? Yeah. I should say some things about these conformal blocks, these Witten blocks, which will be useful for the later, some of the technical thing. That what is the structure of this Witten diagram? So it will, up to some proportionality, these can be expanded very simply in terms of the usual conformal blocks. I will denote the usual conformal blocks by G. So this Witten conformal Witten diagram thing that you compute is essentially the conformal block of the same operator delta and L, but then there's a sum over, let me see, how did I denote this? We are looking at, for simplicity, identical external scalar operators, so I'll stick to that. Case Is this visible, by the way, in the HRI? The bottom of the blind? Okay, I'll write it as, this is visible, this size?
Yeah, well, now nothing is visible because it has become one spot, but actually it was visible.
It has become, okay, when you talk, okay. It's an uncertainty principle, you're affecting your, so, Yeah. So now I hope it is somewhat visible. So what I'm saying is that the Witten block is the usual conformal block of the same exchange operator, but an infinite sum over another discrete family of conformal blocks whose dimensions delta n are 2 delta phi. So I will use delta for the exchange operators, and this one has dimension delta phi, the external operator. So this are a set of operators which you normally call in ADS-CFT the double trace operators, because they have dimensions. But these are not approximate. This is an exact statement. It's an exact mathematical statement that there is a sum over operators which have dimensions 2 delta phi plus 2n plus L prime. L prime is just going is a bounded sum up to L. These, if you wish, in the double trace language, people view them as operators like this. So these operators is with 2 phi's and del to the 2n, del to the L prime with various tensor indices. This is del squared to the n, so this is, and then the derivatives distributed in some way so that it's a primary. This operator, so there are a class of operators, or mathematically you can just think of a conformal block labeled by operators with this dimension. And there is a piece which is derivative of that block, and that's simply coming from the fact that you have identical external operators. If you didn't have identical operators, you would have had blocks with, if you had phi 1, phi 2, phi 3, phi 4, you would have had things with delta 1 plus delta 2 and delta 3 plus delta 4, but when they're identical, you have to take a difference. So they would be it would be the usual sort of things, and this is what gives you the logs, for instance, in the usual ADS-CFT. This term gives you the logs. No, there. Yeah. No. W is what I will use for the Witten diagrams. GS is the conformal block. And these are also conformal blocks. Conformal blocks are kinematic objects. They are labeled by just the dimension and the spin, with external identical scalars are assumed. And so this is that function with delta and L as its label. These are functions with delta n and L prime as their labels. And this happens to be just a derivative of that function with respect to delta, delta evaluated at delta n. So it's just a derivative of that.
Second part does not depend on the operator value?
No, this part doesn't. The coefficients will depend, might depend, but not, the conformal blocks won't depend on the external operator.
N runs from 0 to infinity?
N runs from 0 to infinity.
L runs from 0, L prime runs
from 0 to L. You have a maximum spin which is exchange. So this is the S channel piece. I have just expanded just to show, maybe to go back to Abhijit's question, that here in this basis you essentially have the original operator, but you have a discrete sum of some additional operators, which are these, what I will call these spurious double trace operators, just to distinguish them from in cases where we will consider physical double trace operators. Physical double trace operators will have an anomalous dimension, which will be proportional to 1 over n. And in the normal ADS-CFT, this term is interpreted as a contribution to that physical anomalous dimension. But I'm not making that interpretation here. It so happens there that you can interpret this as the first term, but I'm not doing that.
And if you take a given contact term, you can also expand it in this form.
Yeah, so I will come to that. In fact, before that, let me talk about the T channel. So the T-channel diagram is purely, yeah. Here, this sum over delta, yeah.
Yeah.
Yes.
So you are again coming over some additional besides.
Yeah, so okay. So this term, there's one for each delta, and that will be, so if you put this back in here, there'll be one term which is like this, which will be a distinct operator you're summing over. But this term will be the same because this doesn't depend on delta. The label here is delta n, which is just 2 delta phi, the external operator plus 2n plus L prime. So this piece will be there in each of these terms in this delta n. So that's the same set of operators which will get contribution from each delta term in this sum.
Okay. But that, however, delta will also include a contribution from delta.
Exactly. So each term in the sum will have a contribution from delta n. So these functions will be common for each term. They'll,
But I'm saying that, however, delta that you had there,
yeah.
that will also include the same delta, right?
No, there's a delta n which is independent of delta. This function is independent of the external label delta.
I think Ashok's asking, is delta n part of the physical set?
Yeah, no, delta n is just happens to be an operator which has 2 delta phi plus. In fact, those are the spurious or unphysical operators, which in general in a theory, in general in a theory with external operators of dimension delta phi, you do not expect any operators in the spectrum to have exactly dimensions 2 delta phi plus an integer plus another L prime. The only exceptions that I am aware of are in a free field theory, or where there are maybe some supersymmetry or something and there's some chiral ring or whatever and the dimensions are additive. Apart from, and in those cases you can deal with those contributions separately because typically those are protected and you can deal with them. So apart from those, in general, there's no reason for there to exist in the spectrum operators with dimensions 2 delta phi plus 2n plus L prime. Yeah? Yeah, it's always primaries. Whenever I talk about the labels, I'm talking only of the primaries. The descendants are always captured in the conformal blocks.
Just to read the thing.
Yeah, sorry.
The summation index is
Here?
L prime.
N L prime, yeah.
L prime and it goes up to L.
Up to L, yeah. The sum over the L prime is from 0 to L.
But sum over n goes from 0 to
N goes from 0 to infinity. Because they are operators of this kind, and any number of these derivatives, but the spin, there's a maximum thing that you can have in the spin.
So if the same structure is repeated for all delta n, isn't there some convergence to
So yes, so that's the whole, so I'll come to that later because we will be demanding the sum over these things to vanish, and you have to, and it has to be a sum which converges. But this is not the only piece. So this is only the first term I've talked about so far.
Sorry, one quick question, that is, in the limit that delta, the intermediate dimension goes to infinity, does this diagram reduce to a particular, reduce to
Contact term, yeah. So, so the T-channel diagram is known to be, the T-channel diagram is known to be just the last kind of term. But now the sum is over all L prime, and you can have, you can have, so I don't know, okay, let me just write it. It's the same thing anyway, since the bottom part was not very visible.
Oh, I see. Then I missed. The T channel is not
just that, yeah, this one. This is the T channel. So in the T channel, but if you expand it in the S channel, these are S channel conformal blocks. These are S channel conformal blocks. So the superscripts always refer to the channel.
So then you don't get the first term.
You don't get the first term. You only get double trace terms in the cross channel. I'm just reviewing stuff. This is, yeah. Oh, this other part of the board, yeah. No, that's cut off.
HRI also can't see the other part of the board? No. Yeah, it's a camera.
The camera, which is.
Good.
They have to
I'm not touching it. Yeah.
Who is moving? Who is controlling? From HRI or both? I mean. Shiraz says, why not?
Sorry, Ashok, when we move the board, can you see the whole board, Ashok? Or no?
Yeah, because it's, I think, what we can see there only.
Can just draw a line then? Or
Yes.
now?
Now it's zooming out. That's not good.
But it's legible. I can cut off a part of the board.
Start reading it full screen and okay.
Oh, okay. When it becomes full screen, yeah, you can see it. Okay, yeah, fine. But then they can't tell us what's wrong.
Okay, you start speaking and then.
Yeah, is it? I hope it is better now. You can put a thumbs up if. It's so. So the.
Sorry, but
right.
you're reviewing, but it's very clear review, and where is this given? I mean, just to read all this.
It is Rastelli and others, I think, are probably the papers that first studied this. I think Friedman, Rastelli, and yeah. They expanded in terms of conformal blocks, and I think, yeah, I think that's probably the best place. I mean, the original place. So the T and U channel both have this kind of expansion. No, it is not. In this channel, it is not, because you can sort of in that this thing it is bound. It is unbounded.
There it was bounded by
L.
is it?
Yeah.
I see, I see.
If you write it in terms of T-channel conformal blocks, again you will get the same kind of structure? Yeah.
I mean, it'll all be reversed. I mean, if you write it in T channel, then there would have been a T channel block like this, and yeah, just the indices permuted. But I'll fix with S, and so so in fact, by the way, this thing is what I will call the kind of crossing kernel. It's the analog of the sort of things that people have been studying recently, and which Abhijit wrote a nice paper on studying the expansion of the conformal block, the S-channel conformal block, or the T-channel conformal block in terms of S-channel conformal partial waves, actually. So this is a similar object because you're looking at the T-channel. I mean, I'm expanding it in terms of definite conformal blocks in a given channel, because the conformal blocks depend on the channel. Yeah, so that's why there's a GS. So WS, when I expand in terms of S channel, there's a GS of delta L, and then GS of all the others. But the T channel has only the S channel blocks of the double trace operators. No, they are all spurious. It's the same delta N and L that I wrote over here. It's the delta N, let me write it again here. It's 2 delta phi plus 2N plus L prime. It's the same same set of spurious poles, they appear. So that's the nice thing about this basis. You are kind of adding a set of operators which is minimally extending the usual conformal block, this thing. Going back to that discussion earlier, you don't have some sum over some crazy things, and yeah.
So the original expansion was motivated by having manifest crossing.
Which it has, right? I mean, because it is STU sum.
But if you are default to S channel and T channel.
No, it is only when you choose to expand that crossing symmetric answer in a particular channel.
Oh, I see.
This A of UV is crossing symmetric, and I expand it in a crossing symmetric basis. But now I want to see how it would look like if I were to expand it in S channel.
Okay.
What is the L prime sum? So can you explain once more that the L prime sum here is unbounded? I mean,
Because essentially there is the exchange here was the spin was L. So that was a sort of a bound of the way the two scalar, they can have some orbital angular momentum, which is sort of the two delta phi's have some orbital angular momentum, which is bounded by L. But now here, you're not coupling those directly. There's this and this that would have, I mean, this and this have spin L. So there's nothing here which tells you that the angular momentum is
so in P and U channel, this Witten diagram, the delta and L dependence is just in the coefficient.
Yeah. These coefficients will depend on delta and L. Each term in this thing will give a different contribution.
So WS instead of what you said was if you wrote expanded in D, if you expanded the WD in D channel, you would have got a similar expression as you got for WS. And so since you know the conformal blocks, you could set up a, you would also, this expression written in D channel is equal to this expression written in N.
Yeah, just interchange the labels.
And you can set up a crossing for even
Yeah, you don't get anything new because it's just an interchange. It's just S and T in the superscripts just interchange, and you'll get those equations, and it's there's nothing new there.
you can algebraically prove that this expression is valid.
Yeah, meaning it's just a relabeling in some ways, no? I mean, because it is what you're calling T channel and you're expanding in a cross channel. It's the same quantity, whether you view it this way or this way.
Just in response to Gautam's question, is it right to say that if you cut the T channel
Yeah,
and
yeah.
S channel, what you get is basically a two particle state?
Yeah, exactly.
So that can have arbitrary momentum one particle way out.
This one, if you cut it here, these are the two particle double trace operators that are there.
So that's why you're not, in a sense, seeing that.
L, because here you see L, because it is coupling so that it has angular momentum maximum L. So was unbounded in that one, but bounded in this one. The T channel and the contact terms also, these contact terms, also for same reason, if you wish, this cutting reason, can be expressed purely in terms of the double trace. So each of these, I won't write it all out again, each of these terms will have a similar expansion in
But is the derivative term also there when you expand the contact?
yeah, it will have to be there. Because it'll be phi 1, phi 2, phi 3, phi 4. You could have, in general, if I had phi 1, phi 2, phi 3, phi 4, I would have the phi 1, phi 2 block.
Yeah.
Phi 1 plus phi 2, instead of 2 delta phi, I would have delta phi 1 plus delta phi 2. Here, this I would have had delta phi 3 plus delta phi 4. But those two coincide. So then you have to take sum and difference.
So that
Yeah.
so these coefficients that you have integrated,
Yeah.
do we know from are they constant? In some sense, or
No, not. I don't think they have any. Yeah, not in general. I mean, it will not in general. I think.
So even the edge block conformal, when you take the edge Witten block,
Yeah.
edge channel Witten block, and expand it in terms of edge channel conformal block.
Yeah.
Do we know what happens to the
Yeah, well, actually, if the C delta L's are the positive ones, and then I think, yeah, these factors are probably assured to be positive in. No, there's a multiplicative C delta L multiplying the whole thing, but yeah, these it's independent of these factors, but. No. No. In general, I don't think there's any positivity in any of. There's no general theorem because in general these are proportional to the anomalous dimensions, and anomalous dimensions can have arbitrary signs, unless there are some very specific cases where it doesn't. But in general, sorry.
Even the coefficients appear in the edge channel Witten block expansion.
Yeah. No, I don't think so.
So they are not all positive because it is cancelled.
Right.
But is it like the external thing is positive? Well,
No, I don't think so. No, in fact, no, I don't think that's the case.
Even the coefficient of just this one, just the first term, the third term.
This one. That, of course, this is a normalization factor which is positive, yeah. Because that's necessary, because that's the physical factorization. Yeah. This is some stupid normalization. Right.
And the empty brackets over there and the empty brackets over here are the same?
No, they are in general different. And in fact, these are much simpler to obtain, and these are much more complicated. They're dependent, and in fact, that's why the crossing kernel is a very non-trivial thing. To expand this, finding these is very challenging. These are relative. These are known. These were known earlier.
You do that by re-expressing this in
Yeah, the T channel, and to find that, I mean, just mathematically and everything. In fact, it's very interesting. These depend in a rational way on delta, whereas these depend in a transcendental way on delta. So anyhow. Yeah, well, actually, in the case of identical scalars, T and U channel will give essentially similar contributions. So, yeah, there was something I wanted to say, but I think. So this is just the basis we were talking of. Sum over L will be bounded by, yeah, I'll come to that, depending on the contact term, this thing will be a bound.
So in particular, that means that in that sum over L there, as delta goes to infinity, the higher terms.
Sorry, what?
If you expand the T channel Witten diagram, in the S channel blocks you had all L's, right?
Yeah.
But when the intermediate delta goes to infinity,
Yeah.
higher L's must be.
Yeah, in general also, even for any fixed delta also, the higher L's, there's a 1 over L to some power fall off. I just wanted to answer you said about the contact terms, you were asking whether this term is there. This is the term that gives the anomalous dimension, so, yeah. Okay, so far I have not told you anything. Let me start the seminar. So the constraints in the Polyakov-Mellin bootstrap is basically at this stage to ensure that in this sum, the contributions of so we demand that the net contributions of the spurious double poles. Is this side, I hope, visible? Vanish. So the net contribution, sum over S, T, U, contact terms, the net contribution. So there is, this piece comes only from the S channel. So that is supposed to be the physical piece. So that tells you that this C delta L is essentially proportional to the original operator. See, but then there's a lot of additional pieces, a whole family of these. So for each N and L prime, term by term, they should vanish. Because the statement, what I have essentially told you is, if I put each of these expansions back in my original expansion, it tells me that the full 4-point function is a sum over conformal blocks in the S channel. So what is, when I get back, I'll get an expansion of the full 4-point function in terms of a set of conformal blocks in the S channel, which is what you normally do. But in the normal case, you have only a sum over the physical primaries. And as I said, barring exceptions, these are not in the spectrum. So their net contribution should vanish because they are not in general in the spectrum. So when I expand the full 4-point function, they shouldn't be appearing.
You don't want to take the contribution from contact terms, it's all of them added?
All of them added. This, all of these added with the right C delta L. That's why these give constraints on infinite set of constraint equations on delta and delta I Cij. Because Cij is essentially proportional to the C delta L. I should maybe call this C tilde. So it gives constraints, and assuming these alphas are determined in terms of these, so these give you infinite set of constraints on these. Only for a certain weighting of these, for certain deltas and C's, will this piece, will these things vanish. Yeah, it's a little confusing. I mean, what I meant is that for each such delta n L prime, there'll be, this one gives a finite number of contributions, but when you sum over all L, everything you get contributions from L prime equal to 0 to infinity, and for each L prime you want to,
Including the sum over L outside.
yeah.
But the argument that these are not real operators in the theory with that kind of dimension. I mean, what I mean to say is that you have the G plus the derivative of G. So it's more or less like the original operator is there.
No, original operator, no.
Meaning that, I mean, that derivative term is supplying the anomality after all. Right? So
No, there is no here, in this way of doing it, there's no anomalous dimension. This is a spurious logarithmic dependence. There is no log square piece. There is no log cube piece. In the ADS CFT, this anomalous dimension is the expansion of u to the that operator plus gamma, and you get log and log square. Yeah, so here it's a spurious log dependence. So to disentangle these constraints, this is some I've just told you a scheme in which you get infinite number of constraints, but how to usefully do anything with them, and this is where I think Polyakov couldn't go very much further, but it appears that Mellin space allows you to disentangle these constraints and at least give you more power in extracting consequences from them. By the way, I must say there is some unpublished work or to be published work of Daniel Mazach and Miguel Paulos, who have, at least in in one dimension, but their general approach seems to be very probably more general. They argue that this approach is equivalent to the usual conformal bootstrap approach. And in fact, these Witten, these things give you what there have been a series of papers. I don't know whether you people talked about it in your journal club by Mazach and Paulos and combinations on the so-called extremal functionals. This is inspired by the usual Richkov et al. Idea that there are, you want to, in the usual bootstrap approach, you want to view the crossing symmetry equation as a sort of as giving you constraints by acting constraints on the OP coefficients and delta by acting on by thinking of it as a functional which you act on functions of u and v, and such that you demand that it has to be equal to 0 or whatever positivity when you act on arbitrary functions of u and v. Richkov et al. For the numerical implementation did a very crude implementation of these positivity conditions by, in a way, looking at their action on u to the n, v to the m, or whatever, expanding around u equal to half and v, some Taylor series expansion basis of functions of u and v. So they looked at it in a, what Mazach and all argued earlier, nice papers, I think, that you can try to be cleverer and talk of what are called extremal functionals, which have a very nice properties of positivity and such that they are in some ways an optimal basis of in the space of functions that you can act on to implement the positivity criteria. And he actually shows, Mazach's paper then shows for one dimension how to implement it and get constraints. So they followed that up and they no, one dimension, just 1D conformal blocks, because 1D blocks are the simplest blocks in some ways. So they want to claim, according to at least the unpublished notes, that in some ways these are very closely related to these extremal functionals. So, and they can relate it to the usual crossing symmetry equations. They claim, at least in certain contexts, they show are equivalent to these constraints. So these constraints are apparently seem to be nothing to do with the usual crossing symmetry constraints, but there is good likelihood, and even Ananda had some papers in some large spin context and so on, that the equations become the same for reasons that that time seemed just not very clear, but maybe this Mazach and Paulos' approach will shed more light on why they are equivalent. That's just a tangential comment.
You expect them to be.
You expect them, but
yeah.
I mean, yeah. But it would be very nice, I think, if this extremal functional this thing, because then it would, in a way, give that even that functional thing a very nice this thing, that there's a to the analytic bootstrap in some sense, and tell you what is the most optimal way of doing the numerical bootstrap in some ways also.
Conceptually, what is the thing that you show there in order to show that equivalence? Because it seems that the way you have argued, you would get the right expansion in terms of conformal positive crossing symmetry. So what is the element that?
No, it's not obvious that it is the same. I mean, I agree with you, and that is the spirit in which we have been pursuing this. But no, but you would like to see that this is not, for instance, fewer constraints, or I don't know. I mean, maybe you are missing something. So the approach in Mellin space is to use the Mellin representation of these amplitudes. Which I'll write in the following way. this is essentially a Mellin transform of in the variables u and v to a new set of variables s and t. And this is a kind of what is called sometimes a measure term. It is just, I'll write it down because it's sort of important. It's for the identical scale. Is this bottom of the blackboard? Is this gamma square of minus t visible?
No, it's not very visible.
Okay.
Somehow it has,
This equation?
okay, now I get
No, this one or this way. Yeah, this one also, I see.
So that screen is flipped.
Yeah, so we, so how do you, just keep talking and it'll, okay. Is it visible? Is it visible? Very good. Okay. So that one is visible. So I'll just write this measure factor rho delta phi. So this will be what is called the Mellin amplitude. So as I said, this is the term which you separate out, and that's the this is a fixed function which you separate out for various good reasons, which I will not really talk about. And then there's this piece which is what will be called the Mellin amplitude. So you can always write this because there's some function of s and t. I separate this out and then so now, so this Mellin representation has many beautiful properties, the least of which is that it has a nice flat space sort of intuition and limits. They play essentially the same role as usual s and t variables in scattering amplitudes, many nice things. So, but let me try to tell you about the various ingredients. So we'll just translate everything that I said now into constraints in M of st. Instead of talking of the constraints on the A of uv, we can translate everything in terms of this. It just requires you to write down the Mellin transforms of each of these ingredients here. So the Witten diagrams, I'll call them M delta L st. So if you wish, the curly M is for the full amplitude, but when it comes decorated with all these indices, that's a very specific amplitude for the exchange of this delta and L. So one of the things we did in this paper is to, so this is, by the way, anyone who has computed Witten diagrams will know that it's not easy to write these quantities explicitly in position space. In fact, the original conformal blocks themselves, while they have a series expansion in position space that thanks to Dolan and Osborne, and also thanks to them you have explicit forms in d equal to 1, 2, and 4, but not, for instance, in d equal to 3 for the Ising model, or in general, so for 4 minus epsilon. So the conformal blocks, all these things in position space are very difficult to work with, difficult objects to work with because you don't have very explicit handles on them. On the other hand, in Mellin space, all the things that we've said will have very explicit, if somewhat hypergeometric form, but they will be some things that Mathematica can handle and so on. So in fact, when we started working on this problem a couple of years ago, that time Mathematica coincidentally brought an update in which it included Mellin transform as a as a new command or whatever it is, built-in function. So.
So the issue is being able to do the integrals to go back to dv?
Yeah, if you were to wanting to write that in that way, it's a bit like, again, position space and momentum space in quantum field theory. We rarely work with position space propagators or anything which are god-awful. But momentum space, yeah, the integral is the problem. So. So one of the things we did in this paper was, people have explored this from the beginning of the ADS-CFT, this thing, and there were fairly, there were some forms for it, but actually we exploited the fact that we exploited this freedom that I was mentioning earlier about in the choice of this Witten diagram. So the freedom is essentially coming from the cubic couplings that are there. And so you can, when I say the Witten diagram, I was cheating a little because I didn't specify what those cubic couplings were. Normally, okay, there's a minimal coupling that people use, and you could think of that as your canonical Witten diagram. It turns out that's not so useful for us. I mean, if you do that, the expression for Witten-Mellin space is more of a mess. So we used a slightly different prescription, which is the same as that up to contact terms. I won't go into the detail. It has to do with, there's a split representation that you have of when people compute these Witten diagrams, there's this sort of a very neat way in which people compute. I mean, this sort of just more for the experts. People write it in terms of some. You can write the bulk-to-bulk propagators in terms of bulk-to-boundary propagators and integrated over and sum over all the different exchanges here and so on. It doesn't matter, but what I will actually use is the final form for it, which.
About that, suppose we think flat space S-matrices, then the on-shell pinpoint coupling between three things is just completely fixed diagram. But the off-shell part maybe has something to do. And since you're integrating
yeah. That's where, yeah.
You mean the on-shell pinpoint is fixed from the SD?
No, kinematically. Because you have p square, all the momenta are on shell. So then there's very few structures that you can have, tensor structure.
Spin S is completely right. But off shell, of course, there's something.
So, yeah, I mean, it's fixed up to some, there will be some over still this thing. I mean, even the string theory gauge amplitude, for instance, has higher derivative corrections, right? Even the cubic couplings have some higher derivative corrections.
So the momentum dependence, everything is fixed up to one overall number, I would say, right?
There's some, isn't there a couple of different tensor structures that you can have? No, not spin zero, but more general. Yeah, but here in this particular case, 0, 0, S. Yeah, so in our paper we give one way to do it for not just spin 2. In fact, spin 2 we work out explicitly a little, but as general case also there is a way to do those integrals. Basically it's an integral over the spectral parameter. That's why it is called the spectral representation. There's a, yeah, anyhow, the technical details I won't. This thing, I'll just write the final answer because the answer can be understood in some ways in a reasonable way. The answer is So there are three ingredients. One is just a simple denominator. By the way, this delta minus L is the twist. So sometimes I'll call it tau, tau by 2 minus S. This is a polynomial, I will say a little bit. This is a hypergeometric function, and its dependence on the S variable, it depends only on the S variable. The T dependence is purely in the polynomial, but the S variable has this thing. So this is a hypergeometric function of the 3f2 kind, so it has 3 parameters in the numerator, 2 denominator parameters, and it's all evaluated at argument 1. But which one? This one, yeah. This times this. So this is this is what is called the Mach polynomial. Because it was first introduced by Mach, who actually introduced the Mellin representation for CFTs. This is a kinematic polynomial. It depends on this delta. This H, by the way, is d by 2. I mean, that's the, if you have seen any conformal field theory paper, H is for half, so half dimension. Sorry? AL is just some 1 plus delta minus L by 2 minus delta phi. And just some fixed number. It depends on the dimensions. So the S dependence is actually here and here, the non-trivial S dependence. And then these are polynomial of degree L. Degree L in both variables together, maximum degree L. It is related. It is not exactly that. Yeah, it's related. There is, instead of this, there are some, the P also appears there. I'll just maybe come to that in a moment. So this is at the moment a polynomial, and
sorry, quick question on that. You know, if you've got a, let's say you've got a bulk Lagrangian, and you do a field redefinition, then that won't change the on-shell 3.1, but will change the off-shell 3.1.
Right.
So you could probably go from one to the other by a field redefinition.
Yeah.
At the expense of introducing 4 point.
Yeah, contact terms. So that's what the ambiguity is.
Yeah.
So we'll choose a canonical form of the 3-point function and push everything into the contact terms. So so this the main thing you should take away from this is actually that as a function of S and T, it's a meromorphic function. Meromorphic, I remind you, means it has only this the complex plane has only poles. Simple, no branch cuts and so on. So it's basically this polynomial of S and T, same thing. So if you take this polynomial out, this thing is actually can be written in the following way. Very simple. It is a sum over poles in the S variable, which are indexed by a single integer n. So the poles are at S equal to delta minus this twist by 2 plus n. So the poles are at these SNs, which are the twist by 2 plus n. These poles are nothing but a reflection of this, this statement. Because, sorry, not of this statement. This is of this one. Sorry, this and its descendants, I should say. Yeah. The role of that will come soon. This poles are essentially the fact coming. So this piece, if you wish, is essentially coming from here. It's the poles which are in the. So you can show in general that in Mellin space, the poles in the S channel are correspond to the operators that are exchanged, the twist of the operators that are exchanged in that channel, plus integer for all the descendants. So these these things are so these are some numbers. So basically the structure is very easy to see, because if you even for a moment remember your African or wherever it is that you first encountered hypergeometric functions, these hypergeometric functions of these variables have a sort of a gamma function of the numerator divided by gamma function of the denominator parameters. So this notice is just differs from this by 1. So gamma function of numerator divided by gamma function of denominator, you will just, and plus n when you do a series expansion. So it just gives you these poles. So it's very easy to see that you have these poles. Yeah. Yeah, I mean, because you're including in a way quantum effects in all the double trace and other primaries. I don't have a very good answer for this question. I can only say that it's something like some tree-level effective action expansion or something like that, because you're including the quantum effects by summing over all the loop parameters. I mean, you can say, after all, when we write the normal this is not really a tree diagram of anything, right? When we write crossing equation, this is equal to this. It's not a tree diagram in some sense of anything. It's just a representation. And here, it is true that these objects have an interpretation as a tree diagram in ADS. Maybe there is a meaning to that. Maybe not. I don't know. So let me come to that. So the measure piece, is, you see, so what do you do when you do this integral? So one way, this is an integral in the complex plane, which is along some vertical contour like this. And there are these S. I showed you one set of poles in the S variable like this, integer spaced, right? These SNs, they go off to infinity like this. So you can think of doing the contour integral, closing the contour like that, and picking up all these poles. Those give you exactly, and that's how you show that those give you the first term over here. That gives you the conformal block. So it's coming from here. And you get the conformal block because you get exactly the contributions of this thing. But you also have this measure factor here. That measure factor, what it does, you see the measure factor also has some poles in S. So those poles are also at S equal to, so there's a S prime n, which is at delta phi plus some n prime. Right? There's another set of poles also here from that gamma function. In fact, there are double poles because gamma square. So you see by comparing, that corresponds to operators of twist 2 delta phi plus n prime. So those are actually the contributions. So this measure piece is what gives you all the double trace contributions in some sense. The nice form of M of ST tells you, I mean, M of ST in some sense knows only about the physical poles. I mean, this piece, M delta L of ST knows about this. Then the additional contributions from that I had just wiped out here from those delta n prime is all coming from this. So there are these two sets of contributions. And that's why it's very nice, because in writing it in this way, in a way, the double trace part gets kind of factorized out in some nice way. That's one of the nice things that happens in this Mellin space.
What to make of that second round function
That, if you wish, is on the other side. So if I close the contour on one side, any fixed t, those poles go the other way. So
So now cancelling these poles is just
yeah.
cancelling the residue.
So I'll come to that. Before that, I want to say one more thing which is important, which is these polynomials that I had. These polynomials have a very nice property, these Mach polynomials, that if I evaluate it at these poles, at s equal to, let's say, Sn, right? This first set of poles. I'll get something which just depends on t. It's also a polynomial in t of degree L, and I'll denote those polynomials as, I think, q delta, I think. Anyhow, whatever the notation is, not, I might be messing up the notation slightly, but anyhow, it's some polynomial that depends on L and N, because there's an N index here, QLN of T, which are known polynomials, and in fact the n equal to 0 piece, which is sort of the primary contribution. These are a set of known orthogonal polynomials. QL0 of T are what are called continuous Hahn polynomials. If you pick up your favorite book on orthogonal polynomials, you will find these are among the more exotic orthogonal polynomials, but whose properties will be very important for us. The orthogonality will be very important. They are not as exotic as you might might first sight think, because actually there is a certain limit in which they reduce to the usual spherical harmonics polynomials, the Gegenbauer polynomials in arbitrary dimensions. In some ways, they are like the spherical harmonics, and that's why we call this a partial wave decomposition. Because this expansion, it's very much like in flat space. In flat space S matrix, just saying you consider on-shell 4-point function S matrix, it will factorize, and the residues at the different intermediate channels, the poles, the residues are proportional to the spherical harmonics in the other variables. Supposing you factorize in the S channel, will be in terms of the cosine theta or the t variable, t by s variable. So this is exactly the same. This is the poles and then the residues, which are the spherical harmonics, which are the right residues that you would have in that channel. There is something, another set of orthogonal polynomials called the Hahn polynomials themselves, and some parameter that becomes continuous. Yeah, I don't remember the exact.
Sorry, I should have asked you about that. There's a sum over n in that formula, and delta n is equal to what? The little n is what?
Where? Little n is not
delta
here.
minus
Here only little n comes. Here there's, this is h. H, which is, this is, that's just a delta minus h is the, h is d by 2. It's
h is d by 2,
right? It's the new parameter, which is the thing that, anyway. It's delta, you can label it by delta essentially. So, yeah. Yeah, maybe I shouldn't have. Okay, so that these are the, and so this, we will use this representation, which is a very explicit representation of the S channel. I've told you the S channel Witten block, how it looks like. And now actually having it in this form, it's very easy to do all the T channel and U channel also. All you do is permute. there's a simple permutation, I think. If you want to go to the S channel, you just replace S to T plus delta phi and T to S minus delta phi. Just take this function, do this substitution, and you'll get the T-channel Witten diagram. The similar one, you get the U-channel Witten diagram. So I've told you essentially the Mellin space counterparts of each of the 3 Witten diagrams that enter our story. Okay?
This is being done for the measure also?
No, it is only for the amplitude. The measure will remain. Measure will remain invariant on all this.
I'm not sure because your measure factor gives rise to additional poles, etc.
Mm-hmm.
And when you demand that the residues at these poles all cancel,
Yeah.
that gives rise to some additional.
No, those are the original constraints. I'm just coming to that. Yeah. So those will. So I'm translating right now. The first step is to just translate what I said earlier about that function basis into Mellin space. I've told you almost all the ingredients there. I'll just tell you about the last one, which is about the by the way, since you're all hardcore, this double pole here, I should say there's a single pole and a double pole here. So the single pole is what gives rise to there were two pieces, right? There was the G delta n, and then there was the derivative of G delta n. The single pole gives rise to the G delta n, but the double pole, if you do the integral, gives a log in position space. If you do this integral, you have a double pole, you'll get a log on that side. Log u you will get. So the two terms that give you the G and the derivative of G, each of which we will have to separately set to 0 as our constraints, correspond to the single poles and the double poles that come from here. Okay. So the last thing I want to tell you is about the contact terms. I'll denote them by MC. And now I will parameterize them a little bit more. In Mellin space, it'll be easier to parameterize those contact terms. It's not 10:15, I suppose, no? Unless we've spoken for 24 hours. It's 1 o'clock. Yeah. So So I will parameterize it in terms of following way, which is convenient. Actually, I needn't have written this whole thing.
It was a Hahn polynomial of degree L.
Yeah, so degree L. So so I'm parameterizing now my contact terms in the following way. I'll firstly truncate to an index which will be the kind of total spin exchanged in that contact term channel. Suppose the maximal spin exchange is L in the S channel. Then there are a finite number of contact terms I can write down with that maximum spin L. And that finite number of contact terms is essentially very easy to parameterize in Mellin space because the crossing symmetric quantities, I have to write just polynomials. So firstly, I should say, contact terms translate to polynomials in Mellin space. That's one other very nice fact about Mellin space, that the simplest 5 to the 4th contact term is just 1 in Mellin space. So It is just, it's very simple. It's just that you put this equal to 1, you'll get the D function, whichever that complicated this thing is. So, then there will be derivatives. And each S and T, just like in momentum space, you should start thinking of S and T as derivatives, like P square. So each S has 2 derivatives, each T is 2 derivatives. Each T has, if you wish, a spin. S is, if you're expanding in the S channel, S has no spin. Each power of T corresponds to spin 1. Because you see degree L, spin L. So anyhow, so what I'm parametrizing here is in terms of crossing invariant polynomials of S, T, and U. Crossing invariant polynomial, but okay, S, T, and I could have defined a U which is equal to minus S minus T. So it's useful to construct crossing invariant pieces from them. This is like, if you wish, the it's morally what you would call the ST plus the quadratic invariant. So when S plus T plus U is 0, then the number of crossing invariants is smaller because one relation is there. So at quadratic level, instead of writing S square plus T square plus U square and ST plus T, whatever this thing, just one is enough. The other one is determinant. So this is essentially that quadratic invariant. And at the cubic level, again, there's only one invariant. And I can choose it to be just STU. So it's essentially those invariants, monomials built from those invariants. These, you can now count the derivatives and see. That's why I put this m plus n equal to L by 2. If you look at the T dependence, you'll see that the spin is L. The spin is basically twice m plus n. And the number of derivatives is something like 3m plus 6m plus 4n or something like that. So these are, it's a way of parametrizing higher derivative terms according to the spin. Exactly. They did it in position space in terms of derivatives, but it's much nicer and simpler. But it's essentially the same counting.
And model is the same language.
Yeah, exactly. So we were just inspired by their this thing. So yeah. So that that is this thing. So you can write. So, yeah.
Rajesh, a question. So this A and N, they're all independent.
Yeah, these were what I called alpha earlier. I guess I should call it alpha only. They are at the moment. I'm just parametrizing these higher derivative terms. As we discussed earlier, they should in principle be determined by the conformal data.
So for example, do you know for a given capital L, how many independent alpha men are there?
Yeah, that's just all. All of these are independent. So there are, you can count them. There are, I don't know, some 6m plus 4m. I mean, there's some number linearly in m and n. Linearly in L, sorry. For a given L, there are some 3L by 2 or something, or 3L into L plus 1 by 2 or something. Quadratically it grows.
So does that match the number of terms that you can write in Lagrangian?
Yes, it's exactly that. As was asked, Polchinski, Heemskerk, and so on, they classify the terms. They work in position space in terms of bulk Lagrangians, which have higher derivative terms. And these are precisely those.
Number of terms in Lagrangians up to field region.
Yeah.
So you want to get on-shell capital.
Yeah. So on-shell just equals to S plus T plus U plus 0.
Yeah. Yeah, it's just S plus T plus U equal to 0.
Yeah, but in the Lagrangian, you might write down terms that don't.
Yeah, there are partial derivative integrations.
Okay.
So that's why it's much nicer to do it in, again, in this momentum basis. So now we come to the question Sandeep was asking about the constraints. So I've told you essentially how each of the ingredients I mentioned at the beginning look like in Mellin space. Now I said the conditions we demand here are that all those spurious double trace contributions for each n and each L prime, they vanish. Now that translation, condition is easy to translate now in this language. That is, I wiped out the Mellin amplitude thing, but you remember the Mellin amplitude, there was this rho delta phi times m of st. So now we just demand that the spurious poles at S prime n prime, which is just spurious poles, single and double. Of this whole amplitude vanish for each n, of course, and each L prime. So now what is L prime? We had L prime over there. We have L prime over here also, because we want the poles. These are the poles. There are spurious poles at these values of S. But the poles are functions of t. And the function of t is something that I can expand in an orthogonal basis, which are the partial waves. So I demand that each L prime means the coefficient of, and I will choose to expand in this orthogonal basis, this QL0 of t. And because the QLn of t are not, for any n, are not orthogonal, so I'll expand in these orthogonal waves. So the coefficient of this for each, this for each L prime.
You could have said t to the n. This is just more convenient.
Yeah, this is more convenient because it's orthogonal. So to pick out the conditions will be in some ways nicer. So yeah. Okay, so I hope the idea is clear. I will not, given the time, I won't write it down in gory detail, because meaning gory detail means I won't set up the notation to write it as a mathematical equation. But the idea must be very clear, which is I have this. I write, okay, let me write this thing. I write the m of st as summation c delta L ms delta L of st plus the t and u plus the summation alpha nm m this contact terms. So I expand the amplitude in this way, because this is what each of the Witten diagrams translates to. And this is the contact piece. And now, so I told you what each of these are, the building blocks. I told you what rho is. You take the product. This ms has these poles, and there are these spurious poles here. When you go to mt, so the spurious poles from this piece come essentially from this measure. But when you go to mt and mu, it's a little bit And for the contact terms also, they come purely from the measure because the contact terms are just polynomials. They have no poles in S and T. So the spurious thing, everything comes purely from there. When I multiply this with the rho. Now for the T channel, for the T channel, you will be interchanging this thing. So there will be so now you will again evaluate that at S equal to, so there won't be a pole in so I mean, yeah, the spurious pole will again this thing, but you will want to evaluate this T channel at decompose this T channel. You will not have a simple decomposition like this because this had a polynomial. Okay, let me step back a little. In the S channel, I mentioned this, that the dependence on T is purely polynomial. And the S has the poles. So that's the statement that the thing was bounded in L. You remember in position space, the things were bounded in L. That is the statement essentially. Now when I go to the T channel, I'll make some changes like this. So now the T goes into all this place. That's why the T dependence now becomes transcendental in some sense. It's in this hypergeometric function. And after you'll get poles in T, which is what you expect. But I'm not interested in the poles in T. I'm still interested in yeah. So you have to expand that object in terms of the full partial waves of this QL0. It's still coming from the measure, yeah. Pole in S is still coming from the measure because the measure is what gives all the double trace, spurious double trace contribution. So the whole point is that, yeah, so that's in a way the whole this thing that in this Mellin space that spurious poles always are coming from this measure. The question is then the rest of the amplitude, you want to try to expand that in partial waves and evaluate it at the different poles.
So you're just taking the whole thing, evaluating at given value of S. In the S channel, it's the dependence in T is some polynomial, so it's easy to expand these guys. In the T channel, it's a more complicated thing, but anyway.
You can expand it, and that's where this crossing kernel comes. And so that's where, in some ways, this actually gives you a solution, though this is not what we were setting out to do, but it actually gives you a solution. This Mellin space gives you a solution for this complicated 6J symbol in some incarnation. In fact, I think you can use this now to get the full 6J symbol because you can apply the same techniques, the same integrals that we did. And the nice thing is, again, this orthogonality. What do you do to extract out this in the for the T channel? You'll take this MT, and then you will use the orthogonality to multiply it with, again, this QL and integrate it, right? So, and let me just say. QL0, the partial wave. So I'm expanding in this partial wave basis. So MT of ST, so in the yeah, but that is relatively trivial because you get anyway these polynomials only, and there's just a finite number of them, so you get this bound and yeah, exactly. So in general, I can write this like this: QS. So actually, I can write it this 2 delta 5. I'll expand it in these orthogonal bases, which are indexed by this spurious pole thing. So anyhow, I have this some something like this. So what I have to do to extract out this, and this is what gives you the residue. I'll just evaluate it as s equal to delta phi because the pole is coming from there. So I just need these functions. I know I can do it at s equal to delta phi plus n or whatever. So I need these functions. This is what is the crossing kernel in this language. The T-channel exchange diagram, I'm expanding in S-channel partial waves. So this is, so to extract this, you just use the orthogonality, some dt of this mt delta L of st, and then q 0, and there's some measure factor of the orthogonality, and so on. And then you do some nice tricks, and basically, to our surprise, we were able to evaluate this integral, and in a way which, hello?
Yeah, question. So in this text, where does the contact terms come in, and what will they be?
Contact terms also, I mean, all of them come in, because there's, all of them in principle can contribute to the residue. So I just told you about S, I was telling you about T, but I can say the same thing. But the contact terms are polynomials for any given alpha mn. The dependence in T is polynomial, so it's an expansion of that polynomial in terms of some basis of polynomials. So it's in principle.
What is the thing to see that the contact terms are necessary? The statement is that if you don't have the contact terms, you cannot cancel the residues.
Yeah, so exactly. So at least we find that in the context of this Polchinski's holographic bootstrap that we need the contact terms to actually implement the bootstrap. And maybe, yeah, given the time, I'll just say that and maybe just close for the moment. So there is this part which is a technical thing, but in the Polchinski et al. Approach, let me just give you a very quick reminder of what Polchinski et al. Did. They were essentially trying to see how in a generalized free field theory, namely one in which you have only, I mean, it's like a large N theory, so you have single trace and double trace operators, but then they considered a simplified toy theory in which you have only a single scalar operator, not even the stress tensor. Just a single scalar operator as the only single primary. And it has some Z2 symmetry, so there's not even any in the 4-point function of that scalar. There's no exchange diagram of that scalar also from a dual ADS point of view. So they considered a theory of these scalars and said, okay, now let's consider a CFT, which is such a generalized free field theory with such a scalar and with Z2 symmetry, and ask what constraints does the crossing symmetry equations put on your anomalous dimensions in that theory, in a 1/n expansion. And what they showed very nicely was that you get a family. Then they also made a further simplifying assumption that let's assume that the maximum spin exchanged is some capital L, that there are only operators of, so let's say we truncate in some sense and have operators only of double trace operators only of some maximum spin L. Then they showed that the solutions to the crossing symmetry equations for such a CFT are parametrized by precisely the set of contact terms, these alpha mn's, all the independent ones which are allowed for that maximum spin L. So there's a family, if you wish, of CFTs, because they are solutions of crossing equation. That's the only constraint that is the family of CFTs labeled by these alpha mn's. And what are these alpha mn's? They are labeling also the possible bulk derivative ADS interactions. So this was the sort of the statement that holographically the CFTs are exactly in correspondence with bulk effective actions for these scalars, but parameterized by a specified number of higher derivative interactions, these in position space, if you wish. And moreover, for any given L, there are only a finite number of these, but what is non-trivial is that you can predict an infinite number of anomalous dimensions with just a finite number of these coefficients. Infinite number for each n. So they can predict, they were able to, what are they predicting? They were predicting the anomalous dimensions of the double trace operators to leading order in 1 over n. And there are double trace operators, as I said, even if L is truncated for any n, you can have double trace operators. So they found these gamma NL anomalous dimensions for all n, parameterized by these, and the same were the solutions of the crossing symmetry equations in the CFT. So there was a one-to-one correspondence between the generalized free field theory CFT and the holographic ADS effective field theories. So there's a 1:1 correspondence between these. So these were solutions of the crossing equation, and you think asking?
So what is the slightly confusing implementation of this program would be if we want to construct the CFT perturbation theory. So in that the correlator is not just given by some of conform blocks, but also derivative of conform blocks. The anomalous dimensions. Then you're constrained that the single pole, double pole should be cancelled.
You mean in a which perturbation? Are you talking generically about perturbation theory, or do you have in mind the generalized free field theory, perturbation theory? Okay, yeah. Yeah. How do you disentangle is your question? Yeah. So that's what I'm coming to, and I will this thing, because now I'm going to say this Polyakov-Mellin bootstrap gives you an equivalent way. You can show that it reproduces in this other very different approach these two answers. And it's not quite the same as this, though it was sort of an ADS like this thing. And this is crossing symmetry, so at least again in this context you see it's equivalent to crossing symmetry. So it was a kind of just a sanity check model. We don't, as of now, reproduce anything more than what they say, and I mean you can't, but within the limitation. But
Contact terms, Rajesh?
Yeah.
Question. So this is statement that the contact terms that you will see is the same as the contact terms that
Yeah. So I will let me make that statement now.
Rajesh, my suggestion is 10 minutes.
Yeah, that statement is what I will just make and conclude. So the statement. Statement is that, so what would we do in as they say, what would Polyakov do? So well, he wouldn't do anything. Yeah. So anyhow, what we did was anyway so in this approach, what is different from so what did these people have? They were essentially saying there are bulk contact terms, and which are labeled by these, and that reproduces the anomalous dimensions here. In our picture, it's slightly different. We have double trace exchange terms here, and in principle, we have contact terms. There's sum over this, and then cross, and so on. All right. So it's different from this. Here, they don't cancel the logs. They have this term, which is, they read off the anomalous dimensions from this log, and that is the same as what they have over here. So here, what we find, in fact, is that if you put in these double trace terms here, and now there are two sets of poles to answer your question. There are the double trace poles, which are the physical poles. So there are a set of physical poles, and then there are the spurious double trace poles. So the physical double trace poles and the spurious double trace poles. They are 1/n separated, the location of the poles. But I can sit on a spurious double trace pole and then do a 1/n expansion on the residue. So I distinguish the two sets of poles which are very close to each other. So there will be, this will be there because in the Witten diagram I'm summing over things. Spurious poles are there because in the measure factor there's that gamma squared delta phi minus s.
And you explicitly put in the dimension of the thing that you have
Is
2 delta plus something.
Plus gamma.
Yeah.
And then I expand in gamma from the residues or whatever. I sit on that pole. I mean, so I'm at s equal to delta phi plus n plus gamma.
So you do the cancellation first and then
Then the expansion. And then exactly the same alpha nm's that appear over here. So the same logs cancel these terms. So in that sense, it shows that, so you don't, it's not even that it's in fact the same coefficients. It's the same coefficients that are there. So it's, in some sense, it's a repackaging of the original thing.
Say that last thing again, Miss, what do you mean to say?
So in principle, so you can say there is these contact terms, and then I need to cancel, right? So there is something here,
Yeah.
which is the double trace OP coefficients of the double trace. By the way, they find not only gamma, but also the OP coefficient.
Yeah.
So there's the OP coefficients here also, which are the mean field plus corrections. And then there are this thing. So, and then there are some coefficients. You want to cancel the log here with this coefficient here, right? That's in our approach. Essentially, it is the terms that are coming from here is equal to minus of this.
So I'm sorry. When you implement your thing, you have to first let's keep your epsilon, your small anomalous dimension fixed. Then you want some residues to cancel. Now you have a lot of data. You have the C delta L's, and you have the alphas. Why can't you do the cancellation with the C delta L setting alpha?
No, you have to expand the C delta L. So you have to see which order in 1/n it appears. So there are, so the C delta L has a mean field part, and then there is an additional part.
Yeah.
So there are cancellations. So the cancellation, so there's single pole and double pole. So there'll be two sets of equations. One if you take appropriate two sets of equations, one constrains the anomalous dimension, the other constrains the OP coefficient, and the correction to the OP coefficient. So the way you would descend, so there would be the mean field answer, which you know so one combination will give you the gammas, the other combination will give you the correction to the C's, so the alphas will be such that that cancellation happens. So you will have exactly, so the way it happened over here, some of the alphas were essentially the gammas, right?
If alphas are 0, then you cannot cancel.
You cannot cancel, so that's why. Sorry?
Is it just they're coming at different orders? Why?
No, because actually in this case to this order the T channel and all don't contribute. It's actually only coming from the S channel. To the first order in 1/n there's an enhancement actually, and only the S channel contributes. So you have to cancel the S channel against something. There's nothing you can cancel it against. And so you have to add the contact term to cancel it. And the coefficient of the contact term turns out to be exactly opposite of that of the original one, and in that, so in this form of writing it, the gammas are coming from here, and so the cancellation condition tells you alpha is proportional to the gamma. Whereas here, you interpreted this as a log u as an expansion, and you said alpha is proportional to gamma. So it's the same. What I'm saying is that it's the same linear relation. There's a linear relation between an infinite set of gammas in terms of a finite set of alphas. The same linear relation between an infinite set of gammas and a finite set of alphas is obtained when you cancel this.
If you had slightly deepened your conditions without including the contact term in that, I mean, I feel that you needed to include contact terms because at the end of the day, you wanted a solution that corresponded to the contact term, right?
No, I didn't put anything in. I mean, I just have to, I parameterize it this way with the same this thing, and then I am forced to have them. If alpha equal to 0 is not a solution unless you put gamma also equal to 0, which is the trivial solution. But if you have a non-trivial...
If you were to weaken this condition that all the double poles should cancel.
No, what do you mean weaken it?
So maybe weaken in the sense that, you know, the solution to the CFT that you get out of because of this contact term actually does have double poles, right? It does have symmetry.
No, not in my approach.
No, not in that approach, but actually, I mean,
No, not in even in that approach. I mean, in some sense, it depends. It's an order of expansion that there's one answer in the CFT. The CFT doesn't have logs. The CFT has some expansion. Now, one second. I mean, the CFT has some expansion. Now I choose to expand the power in 1 over n. Then I will generate logs. I will generate log square and so on. I know from that expansion that the coefficient of the log term is the anomalous dimension. Now, I leave that aside. I come back to my original CFT. I choose not to expand in the exponent in powers of gamma. So I will have, another way to say it is that the full answer is A of uv. Let me go back to position space because we'll have pieces which will be u delta phi plus gamma. There'll be pieces u delta phi. I mean, in my way of expanding it, these will be coming from the double trace poles. These will be coming from the physical spurious double trace poles. These will be coming from the physical double trace poles. The coefficients of these are also proportional to gamma in such a way that, so these are, in my way of this thing, these terms are all there. And I'm not doing anything with them. But if I'm, but I want to set these to 0. And these will have things which are, so that's the same as saying that I'm sitting at the pole corresponding to this, but not the, so this piece doesn't enter that pole. So I could have chosen to expand then afterwards, and I would get some logs there also, but I'm not doing that. There's another set of logs that are here in my approach, which is a different set of logs in some sense. Yeah.
Instead of 1 over n now, if you were to do epsilon for the simplicity, 4 minus epsilon dimension, you would have similar type of curve. I mean, there, how is it?
There are no, at least for, if you're not in large n, there is no such issue, because the spurious poles are not very close to the double trace. Phi square and phi have nothing to do with each other in the Ising model, because you're not at large n.
In epsilon.
Even in epsilon, I mean 4 minus epsilon, phi square operator for in the Wilson-Fisher has nothing to do with phi. I mean the dimensions are not.
It's corrected by epsilon.
It is corrected by epsilon, but yeah, so everything is corrected by epsilon. That's the free field answer. But once again, you sit at the spurious poles. I mean the exact, there will be the, to order epsilon, the dimension is not twice that of this thing. You see, I mean the delta phi square is not equal to 2 delta phi. It is only to leading order. And then there are the leading order. So that's why you have to sit on the right pole and then do an expansion on the residues. It's tricky. I got confused by this for a long time. But because you can think in terms of the poles, there are two very nearby poles. One is a spurious pole, one is a physical pole. I can think of the full amplitude before doing any expansion. I can think of the full amplitude, and there are two very nearby poles. if I start doing epsilon right from the beginning on the full amplitude, I'll get confused because the two sets of poles will mix. But I can look at the full amplitude. I distinguish the two sets of poles. I sit on the residue of the spurious pole, and then do an expansion on the residues. And that's what reproduced. In our first paper, that's what reproduced all the right answers. So that we have a discussion in our paper about the reason why to that order in epsilon, I think the contact terms don't appear. And we, in fact, give this thing that if you want to reproduce delta phi square up to order epsilon cubed, there's a zeta of 3 and so on that appear. To reproduce that, you will probably need contact terms. But how exactly to do that, we don't know.
Sorry, just understand. So suppose you fix a particular alpha m, then you can solve for C, C delta. For any given choice of alphas, you can solve for the C delta. That's how it works.
Yeah.
There's a unique solution for C for any given choice of them.
Yeah. That was the Polchinski solution, and that's what is our solution as well. So we're just reproducing that. But it's a non-trivial solution because it's a finite number of alphas reproducing an infinite number of C's and gammas. Okay, thank you, folks. Only Ashok like yeah, no, few. Okay, 4, there are 3 or 4, I see, yeah. You'll have to, okay. The contact terms don't have any poles. I mean, they contribute to the spurious poles. The contact terms, all terms contribute to the spurious poles, contact, exchange, everything. The physical poles have contributions only from the exchange diagrams. Because the exchange diagrams is where there are physical operators of this conformal data, those operators are exchanged. That is in the exchange diagrams. The contact diagrams don't have any poles, any physical poles. Because this is just polynomial in SNT.
ICTS, any questions?
No, no further questions.
Well, yes, we can continue our discussion over that. That's fine.
Okay, see you.